Hi, welcome back to the second part on Bayesian play. We were discussing an example or a demo in NetLogo. So let's now move on. So we discussed this and we were here. And I owe you an explanation of how the probability of a history is computed given that you know that the reply rule or the strategy of the second player is just 10%. And just 10% is playing tit for tat 90% of the time and playing and defecting otherwise the other 10% of the time. So here a bit of notation. This is the event that indeed player 2 strategy is just 10%. This is the event that the first player cooperated in the previous round. This is the event that the opponent cooperates in the current round. And this is the event, well, I should have indexed this one with T as well, that just randomizes in the current round. Well, let's do that. Let's index it. So I've now added supplemented xi, the event that just 10% randomizes in round T, supplemented with the index T. So player 1 does its own thing, but we are interested in the behavior of the second player and try to predict what he's doing and compute the probability of the history given that he's playing just 10%. Well, the probability that the second player chooses to cooperate in the first round is 1, because at the outside nearly all strategies cooperate in the first round, and just 10% is no exception. Yeah, that's better. Of course, player 2 has a 10% to randomize also in the first round, so the probability that the second player cooperates is also 90% in the first round. So here. So let's only look at this row here. So the probability that the second player cooperates in the first round is 0.9. Tit for tat prescribes that the second player should cooperate in the second round because the first player cooperated in the first round. There's a 10% that the second player randomizes, so this must be this 10%. Now, Joss plays tit for tat 90% of the time and defects 10% of the time, so this is all 90%, because there is 10% time that it plays defect, but it didn't happen here. If the first player defects, then the second player should defect either way, either by randomizing or by playing tit for tat. So the probability that it defects as well is just 1. Now this behavior here isn't explainable by just 10%, because if the first player, we just explained, if the first player defects, and the second player should defect as well. Now here the first player defects once again, so the second player, whether it should randomize or not, should defect as well. But it's not the case, so we can completely rule out this action. The probability of this action of the second player is 0. Now, the probability of the history is this line. It's just a product of the respective actions. So 0.9 times 0.1 times 0.9. So this is the probability of the history. And because each possible path of play, as it gets longer, becomes more and more improbable, because there are many possible paths of plays, it's very natural that the probabilities become smaller and smaller. But just the nature of that there are many possible paths of play. So, and eventually the probability that this history here is of course 0, because this is impossible. So if you want to put it, so how did we have computed this? So for example, well, and these here, the probability that the history, that the history is equal to cooperating in the last round and the rest of the history, given that the first player cooperated as well. Well, they have to marginalize this probability by the probability that the second player randomizes in the current round here. And of course we can say something about this probability in which age is filtered out, because the probability that the second player cooperates in the current round and has played this history in the previous rounds are independent. So we can factor out this probability, and we remain with the marginalized conditional probabilities, well, which we can all compute, of course, like we did so here. So for example, the probability that the second player cooperates in the next round, given that the first player cooperated in the previous round, and given that the second player randomizes in the current round, is 0, because then the second player always should defect, so it's 0. And the probability that second player randomized in the current round is 0.1. And the probability that second player cooperates in the current round, given that the first player cooperated in the previous round and the second player did not randomize, is 1, times the probability that the second player did not randomize, and that is 0.9. So here this computation, for example, applies to this number here, CC, and 0.9 here. So this number here is equal to this number here, or here 0.9 times the probability of the history, so times 0.9 is 0.81. So let's consider another example. A bit of a different nature. We hypothesize now a countably infinite number of reply rules, and these are all unforgiving before t, so indexed by t, unforgiving before round t, and unconditional defection at round t and later. Now, you can't give uniform prior probabilities to those reply rules, because there are an infinite number of them, and an infinite number of finite numbers is infinite, and those probabilities should add up to 1. So this is a possible way of dividing prior probabilities to all those hypothesized strategies in such a way that they add up to 1. So in the first route, player 1 gives prior probabilities to those strategies. And here there are countably many, because you first have that there's no unconditional defection, and then you have the countable row here. Now, if the opponent cooperates in the first round, then we can rule out that it avails himself of the reply rule G sub 1, because G sub 1 already defects in the first round, irrespective of whether the first player cooperated in the first round. So we can rule out that reply rule. Effectively, you can rule out this history, and then through Bayesian reasoning we can rule out this reply rule, and you see that Bayesian updating works in such a way that the rest of the probabilities are maintained in equal proportion. You see? In equal proportion. In such a way, of course, that they still add up to 1. Now we can rule out, if the opponent cooperates in the second round, then we can rule out that it avails themselves of G sub 2, and you see that the probabilities are respected, the proportion among the probabilities are respected in such a way that they still add up to 1. And that is thanks to Bayesian updating. And so on and so forth. In due course, more and more reply rules are ruled out until there is unconditional defection from the opponent in the 5th round. So we know for sure through Bayesian updating that the opponent avails himself of G sub 5, because there's unconditional defection. So that's one side. Now let's switch sides and look at this development of play from the perspective of the first player who tries, from the second player who tries to predict the reply rule of the first player. So the second player tries to predict the reply rule of the first player. So player 2 gives prior positive probabilities in the same way as before. But now the second player tries to predict the behavior of the first player. Now it can rule out by this action here, G sub 1, by this action here. Now because the second player defects autonomously, so it's the first one to defect. The second player, because the second player defects on its own terms, it's the first one to defect, the first player has to defect as well, either due to unforgiving or by unconditional defection. So the course of play and the history doesn't reveal which strategy the first player is using. This is either by conditional defection, because the second player has defected and the first player by unforgiving defects as well, Or it may be that the first player avails himself of unconditional defection in the 6th round. So we don't know that. So as far as Bayesian updating is concerned, we are left with this probability distribution among hypothesized reply rules or hypothesized strategies, and further play doesn't not give further information about this probability distribution. Another example, which is due to the monograph of Peyton Young. So here. The example discussed on page 94. So we have two players who play the coordination game, and they hypothesize over the following set of 3 different reply rules or strategies, if they're called alternatively. Stay left forever, stay right forever, or play half and half randomly forever. And suppose that the two players have the following priors. So player 1 divides his prior in this way, in the first column. So gives the bulk of the probability to that the second player plays a left star, and the second player has priors divided in such a way. Now after the first round, and the second round, we as an external observer can already rule out that both players play either consistently left or right. So must play another strategy, but certainly not left all the time or right all the time, because both have switched. First player from left to right and the second player from right to left. Well, player 2 with Bayesian updating is able to conclude this, to reach this conclusion as well. So the probability that the first player plays right all the time, given the history of play here, is, well, Bayesian updating. Fill out all the numbers. Of course, the probability that this history emerges, given that the first player plays right all the time, is of course 0. Times the prior, which is 3. Sorry, it's 0. Yeah, should be 0.5. I switched the priors of 1 and 2, but it doesn't matter for the example. But at least this is, of course, 0 because of this 0 here. All the other numbers don't matter. And the probability that the second player maps the first player onto playing mixed 0.5 forever, mixed half and half, is, well, the history of this history here, given this one, is of course 0.5 times 0.5 times the prior probability, 0.1. So if I exchange the example with player 1 reasons, then all works out well. So let's change this. So now the calculations are correct and have the right numbers here. Player 1 reasons, because the priors of player 1 are as follows. So because F star capital F star is the only reply rule left. It is given a Bayesian probability of 1 because it's the only alternative. Now, if the second player indeed plays mixed half and half, then the first player solved the problem. But for just as well, for the same reason, player 2 need not play mixed half and half at all. Now, player 2 has reasoned analogously, and so any action is indeed the best reply to mixed half and half because it's a coordination game. So the second player could in fact play any strategy after its observed age because any action is the best reply. So in fact there is, if you temporarily for a moment step away from the Bayesian scenario, player 2 could in fact play any strategy after its observed age. Now the solution may be to extend the set of the set of hypothesized reply rules by an uncountably infinite set of all stationary mixed strategies. So play 10% left all the time, or play 5% left all the time, or play 0.11111% left of all the time. So these are uncountably many reply rules, and this is a larger pool to choose from, and capital F star is an element of this pool. Now the players can update their posterior beliefs about each of those strategies by Bayesian updating, like so. Not only summing over the different p's, because we have now uncountably infinitely many mixed strategies we have to integrate, while exaggerated the notation somewhat to indicate that we're not dealing with summation but with extended summation, which is integration. You see the integration symbol looks like an S of summation. Now, because the best replies on the mixed strategies P intersected with the set of possible reply rules, hypothetical reply rules, this is a closed system of playing and prediction. So this is going to work, because players update their strategy in such a way that it remains within the system. So this is going to work. However, if players do not update according this way, then of course they may avail themselves of all other kinds of strategies. So then it would perhaps be possible to extend S even more and give positive probability to all other sorts of reply rules other than stationary mixed strategies. So in a way, it would be desirable to give as many possible reply rules a positive probability, because then the net you will cast over the behavior of your opponent is very wide. That would be nice. So in the extreme, we would like to give all possible realization positive priors, or all possible reply rules positive priors. Now, unfortunately, this is not possible. This is a consequence of measure theory, and measure theory is concerned with how to give positive real numbers to sets, and in probability theory that is the problem of giving probabilities to events, which are also sets. So it can be shown that the set of all realizations, so this is one particular realization here. Of course, the set of all infinite realizations of all play paths is of course uncountable, and you can easily show it with a diagonalization argument. So the set of all play paths is uncountable. Now the question is it possible to have a probability measure such that you give a positive probability to all non-empty sets of play paths? And it is known that the probability measure must be closed under complement and countable union, and this is called, if an operator satisfies these properties, this is called sigma algebra. And the answer is negative. The set simply is too large. The set of all subsets of all possible play parts is simply too large. And if we would try to enforce this, we would run into all kinds of problems and paradoxes. Like, for example, the Banach-Tarski paradox, which tells you that if you insist on giving all sets, all subsets of the set of all realization of positive probability, then you would not sum up to 1, and then still, if you want to give a subset, then you would, if you insist on this, you would have to rely on the axiom of choice, and that would imply that, for example, from 1 you can decompose one massive ball and then put them together into massive balls of the same volume, if I quote it correctly. I shamelessly copied this image from Wikipedia, like here, Banach-Tarski paradox. The interesting variation, quite stronger variation, is the P and the sun paradox, that says a P can be chopped up and is reassembled into the sun if you accept the axiom of choice. Here. So that's not a solution to give, well, it's simply impossible to give every conceivable subset of possible play a positive probability. So the solution is to extend a probability measure on histories, which is possible because the set of histories is a countable set, to sigma algebra on the possible paths of play. So in order to make the length of this video not too long, I will leave it at here. Thanks for bearing with me so far, and hope to see you on the other side.